So hello everyone. Today's short video is going to be the introduction to now chapter 3, which is acids and bases. And a lot of the material in here should be a review from General Chem, Chem 153. So a couple of things to begin with, the definitions of acid and base. And one of the ones that we used almost exclusively in General Chem was the Bronsted acid and base. And in this definition, a Bronsted acid is an H plus donor, and a Bronsted base is an H plus acceptor, or a proton donor and proton acceptor. So that's the traditional HCl dissolves in water, you make H3O plus, Cl minus, that sort of thing. And I will write a couple of those reactions up here. It turns out that this one is used sometimes for organic, but not nearly as much. An alternate definition, the Lewis definition of acids and bases, is one that we're going to use a tremendous amount and is much more useful. Now, Lewis switches away from thinking about protons and looks at the electrons. So a Lewis acid is an electron acceptor. Okay, so the acid with an A is the acceptor of electrons with an A. And a Lewis base is an electron donor. Okay? And this one turns out to be much, much more useful because most organic reactions, in fact, I would say probably 70 or 80%, do not involve transfers of H pluses, but rather are forming bonds and do all sorts of other things with other kinds of atoms. So again, this one turns out not to be quite so useful. We do have one additional way we describe this. A Lewis acid is also called an electrophile. And a Lewis base is called a nucleophile. Okay, so electrophile, acid base, Lewis acid, nucleophile, Lewis base. Okay, so that's just getting some of the definitions out of the way. At least for this first day, let's focus on the Bronsted again, just to remind you of the things you should already know, and then we'll quickly switch over to Lewis. Okay, so if we think generally about a Bronsted acid-base reaction, right, in the most generic sense, HA, which is our acid, you can think about this dissolving in water, and going to then become H3O plus and A minus, right? So that would be an acid dissolution, an acid dissociation reaction. Okay, this is the acid. Okay, water is acting as the base, right? So this is donating the H, this is accepting it. The A minus, after the H has been removed, is the conjugate base of the original HCl, and H3O plus, after it has accepted, is the conjugate acid. So again, this base goes with this conjugate acid. They differ. This does not have the H plus, that does. And likewise, this big set over here goes together. This has the H plus, that does not. Okay, so that's sort of the fundamentals, and you could do the same thing with a base as well. Now, when you have this sort of an acid-base reaction, right, a Bronsted acid-base reaction, you can think about the Ka, the acid dissociation constant, and that would equal the concentration of H3O plus times the concentration of A minus over the concentration of the original HA acid. Okay, now we are not going to be doing any calculations with this, but just to sort of remind you how you talk about acids and bases. And then likewise, the pKa is going to be minus the log of the Ka value, that's here. Okay? So this is just a little bit about how you would talk about them numerically. Again, we're going to use Ka and pKa just to try to understand strength of acid and base, but we are not going to do any calculations with them. Okay? So give me just a second here to erase a little bit of this, and then we'll talk a little bit about strong and weak acids and bases, Bronsted acids and bases in particular, and we'll look at the sort of Ka and pKa values for those. Okay? So I'll leave that reaction there. So a so-called strong acid, and again, now I'm talking about the Bronsted sense. Okay, this one essentially completely dissociates in water. So a strong acid is going to have a large Ka value, which means it's going to have a small pKa value. And again, it's because of this negative sign here in front of the definition of pKa. For a weak acid, well, it's just the opposite. This will have a small Ka value, which means it will have a large pKa value. Okay, so again, strong acid, large Ka, small pKa, weak acid, small Ka, large pKa. So if we look at just a couple of quick examples, right? Some things that you know are strong acids, you should know these from 153, things like sulfuric acid and hydrochloric acid, those are strong. Then we have some weak things, so something like, for example, ethanol. And then we have some moderate things, something like, for example, acetic acid. Okay, and so it's one of these H's, it's this H, it's this H, and it's this H that we're talking about, right? That's going to get transferred. So for sulfuric acid, Ka is 1 times 10 to the 9th. For HCl, it's 1 times 10 to the 7th. Very large numbers. So what this means is that the pKa for the top one is going to be -9, a very, very small number. That's a very strong acid. And the pKa for this one is -7. Okay? Now for these, this Ka is about 1 times 10 to the -16th, a very small number. So this is quite a weak acid, which means then the pKa is going to be quite large, 16. Okay, and so this is weak, right? These two are strong, this is weak. Acetic acid is sort of in the middle, right? Its Ka is about 2 times 10 to the -5. So small, but not nearly as small like this, and certainly not big like that, which means that its pKa is going to be about 4.8. And again, I've rounded these a little bit, but that's the idea. So very strong acid, weak acid, and then something kind of in the middle. And again, you can see these sort of ideas represented there. Now, one of the things we're going to need to do on Monday is look at other organic molecules, right, to see their acid properties. We're going to need to think about organic molecules as bases, right, and then we're going to need to start to think about acid-base reactions, okay? And one last thing before I wrap this one up. If we think about an acid and its conjugate base, and there are sort of two pairs of those here. If the acid is strong, right, like the top two, the conjugate base will be very weak. They are inverse of each other. So HCl is a very strong acid, Cl- is a very weak conjugate base. If we had something like ethanol, ethanol would be a very weak acid. That would mean ethoxide, the anion, after it lost the H, would be a very strong base. And again, we'll come back and look a little more at some of that on Monday as well. But this is at least now setting the stage for acid-base and acid-base reactions. We'll see you all Monday.